All right, in this problem, we want to find a formula for R sub n. That means the right-hand rectangles, a Riemann sum with right-hand rectangles with n of them, n rectangles, for this function f of x equals 11x squared plus 77x on the interval from 6 to 11 in terms of n. And then we'll find the exact area by taking the limit as n goes to infinity of Rn. It takes a lot of work to get to Rn, and then to get from here to here, that's just one single step where you actually take the limit. All right, so to find Rn, first let's draw a picture just to get a visual on this. So we have our function x squared plus 77x. It doesn't really matter what it looks like, and it's a quadratic. I'm just going to draw it kind of like that. Here's 6, and we're going out to 11. The point is to estimate the area under the graph, and it is positive. We're going to estimate the area under that graph by finding Rn from 6 to 11. All right, we're going to take n little rectangles, and it's somewhat implied that n is a large number. So we need to find the width of each of those rectangles. Now, the width of each rectangle, delta x, is defined as b minus a over n, where b and a are your endpoints. So b minus a is the length of the interval, n is just n, and I typically go with all cursive lowercase n, and I'll just switch back to capital N at the end. Okay, so the width of each rectangle there is 5 over n. All right, for the Riemann sum in terms of n, let's go find the height of each rectangle. Well, the height of each rectangle is different whether you're taking a left, midpoint, or right Riemann sum. And here are the formulas for the x value at which the height of the rectangle is taken, which we're going to call xk bar. So if you're doing a left Riemann sum, the height of the rectangle is taken at xk bar equals a plus k minus 1 delta x. We're doing a right Riemann sum, so xk bar is defined as a plus k delta x. A is the first endpoint of the interval. K is going to be our counter in the Riemann sum, and delta x is the width. So, going back to here, okay, we're doing a right Riemann sum, which implies that xk bar is equal to a, which is 6, plus k times delta x, which is 5 over n. And the height of the rectangle is actually f of xk bar. Before I take f of xk bar, I'm going to reverse this and write it as 6 plus 5 over n k. N is just a large constant, so 5 over n you can think of as a large coefficient of this index k. All right, so now we're going to take f of that, so f of 6 plus 5 over n k, that's f of xk bar, I suppose I should write. All right, we're going to plug this expression in for x here and here. So we're going to have 11 times 6 plus 5 over n k all squared plus 77 times 6 plus 5 over n k. Now the Riemann sum is defined as the sum of the areas of the n rectangles. So the Riemann sum is defined as the sum from k equals 1 to n of delta x times f of xk bar. So in our example, it's going to be the sum from k equals 1 to n of delta x, which is 5 over n, times f of xk bar is this expression right here. So we have 11 times 6 plus 5 over n k all squared plus 77 times 6 plus 5 over n times k. Now we want to simplify this expression, which is going to take a bit of arithmetic and algebra here. Constants we can pull out, so probably the easiest thing to do first is to pull that 5 over n out, because remember n is just a large number, so 5 over n is just a large number, or not necessarily large, it's probably a small number, but it's a constant. And then we can split the summation of this sum, we have two terms here in the sum split by that plus, into the sum of two summations if we want to. although I'm not going to do that quite yet. I think I'll go ahead and expand and simplify this expression a little bit first before I distribute the summation. So for simplicity, I'm pulling out the 5 over n. That's this 5 over n right there. Okay, let's go ahead and FOIL this. I think, oops, leave off the summation sign. Let's go ahead and put the summation sign there so we don't forget it. Summation from k equals 1 to n of everything else here. All right, so we're going to FOIL this 6 plus 5 over nk all squared to get, let's see, 36 plus 5 over nk times 6 is going to be 30 over nk plus 30 over nk is going to be 60 over n times k. And then plus 5 over nk all squared, we'll just square everything, so 25 over n squared k squared. That's all times that 11 out front. This one we can go ahead and distribute the 77. You're definitely going to need a calculator for parts of this problem here. So let's see, let's do 77 times 6 up here. We're going to get 462. Plus, we've got 77 times 5 is 385 over n times k. All right, let's go ahead and distribute the 11 and clean up as we go as much as we can. So let's see, well, I guess I'll just distribute the 11 first. If I try to do too much at once, I'll make an error, and we definitely don't want any little errors here because that would cause the whole thing to be wrong. So we're going to do 36 times 11 first to get 396. Okay, plus, now I've got 60 times 11. It's going to be 660 over n times k plus 25 times 11 is 275 over n squared k squared plus 462 plus 385 over n k. All right. So we can go ahead and combine some like terms here inside the summation. So we still have the 5 over n out in front of the sum from k equals 1 to n of, we got 396 plus 462. So let's do that here. 396 plus 462 is 858. It's adding this and this term. Now looking at this, we have two terms with a single k, 660 over nk plus 385 over nk. So I'm going to add the 660 plus the 385 to get 1045 over nk. Plus the last term is 275 over n squared k squared. So after we have distributed and combined like terms, now we can go ahead and apply the summation rule, which there's two. One says the summation of a sum can be split into sums of summations, and also we can pull constants out to the front of the summations. And then after I do that, I'm going to apply the power sum formulas. So we have 5 over n times, my first one is the sum of 858, which I'll just leave as is, even though it is a constant, that's fine. So we have the sum from k equals 1 to n of 858 plus 1045 over n, that constant I'm pulling out to the front of the summation from k equals 1 to n of k. Maybe we should put some parentheses around these here. And then the last one is 275 over n squared times the sum from k equals 1 to n of k squared. And now we can go and apply those power sum formulas. Okay, here are the power sum formulas. So for the first one, we've got the sum of a constant is the constant times the number n. So we'll apply that one first. That's this right here for the sum of 858. So we have 5 over n times 858n plus for the sum of k, that power sum formula is right here, which is n times n plus 1 over 2. That's times 1045 over n. So the sum from k equals 1 to n of k is n times n plus 1 over 2 plus 275 over n squared times the sum from k equals 1 to n of k squared, which is this one, which is n times n plus 1 times 2n plus 1 over 6. Okay, so now we have gotten rid of all of these summation symbols by finding the summations in terms of n. So now from here we can go ahead and simplify. So I'm going to distribute this 5 over n out and do some simplification in here as well. So when we distribute the 5 over n over each of the 3 terms, and the first one, that n cancels with that n, and we're just left with the constant 858 times 5. Which is 4,290. Okay, plus, then we'll have 5 over n times 1045 over n. Actually, let's not do that way. Before I combine this term, let's go ahead and cancel those n's. And I can do 1045. No, that doesn't divide by 2 very easily. I guess that'll be it. So let's go ahead and do 1045 times 5. Which is 5225. In the numerator we have times the n plus 1. In the denominator we have this n times that 2. So it is over 2n. And let's see, over here that n cancels with one of those n's. And that's about all I see that simplifies at the moment. So we'll go ahead and multiply the 5 times 275 to get 1375. That's the 275 times the 5 is the 1375. Then I have times n plus 1 times 2n plus 1. I'm going to go ahead and FOIL that. So we'll get 2n squared plus n plus 2n is plus 3n plus 1. That is all over 6n. Okay. So we need to keep going here and keep simplifying. So we have 4290 plus, let's separate this into a sum of 2 terms. So the first one is 5225n when we distribute that over 2n. Well, when you distribute and then put it over 2n, the n's cancel, so you just get 5225 over 2. Okay, plus 5225 times 1 over 2n is 5225 over 2n. Okay, then over here, do the same thing. So 1375 times 2 1375 times 2 is 2750. And that's going to be times n squared over 6n, 2750, n squared over 6n. One of those n's cancel, so we're left with a single n in that numerator. Oh, but that's not true. Oh, here's what I did. Down here, we should have had that n, should have been multiplied by that n. I did multiply in the 5, but I forgot to multiply in that n. So we actually should have an n squared down there. There we go. So then we have n squared over n squared, which cancels. Plus the next term is 1375 times 3n. 1375 times the 3 is 4125. And that's times n over 6n squared. So one of those n's cancel, so it's over 6n. And the last one is 1375 times the 1 is 1375 over 6n squared. Okay, we are almost there. So now let's finish simplifying and combining like terms. All right, so the constants are 4290, 5225 over 5, and 2750 over 6. Those are my three constants. And if we try to divide this one, 2750 over 6, it's not a whole number, and it's also not divisible by 2, so we might as well just use 6 as a common denominator here. So my first term, 4290 right here, to put it over 6, I'm going to multiply it times 6. So 4290 times 6 is 25,740. So this term, 25,740 over 6. This one I need to multiply its numerator by 3 to get a denominator of 6. So 5225 times 3 is 15,675. And then I'm going to do this term next, plus 2750 over 6. So those are my three constants. So you have two terms that are over n, 5225 over 2 and 4125 over 6. I'm going to also need to get a common denominator of 6n there. So we'll multiply this one by 3, which I just did. 5225 times 3 is right there. So 5225 times 3 is 15,675. So that's over 6n. Plus this term is 4125 over 6n. Plus 1375 over 6n squared. Whew, so now when we combine all of these, my first three terms are 25,740 plus this one is 15,675 plus 2750 is 44,165 over 6. And the next two are these two adding their numerators. 15,675 plus 4125 is 19,800 over 6n, which might be divisible by 6. I can certainly reduce that. Let's go ahead and see. If I divide that by 6, yeah, that's the same as 3,300 over n. Let's go ahead and change that to say 3,300 over n right here. And my last one is still 1375 over 6n squared. Okay. So that is Rn. That is the area under the curve in terms of n. Under this curve, 11x squared plus 77x on the interval from 6 to x. So all you have to do to take the limit as n goes to infinity to find the exact area is one more step. So then the limit as n goes to infinity of Rn is the limit as n goes to infinity of this, but that term will go to 0, and that term will go to 0 because their denominators have n. So you'll just get the exact area, which is 4,165 over 6.